Okay, now I'm okay, good.
All right, so we see your screen. It's not full screen presentation mode.
Exactly.
There it is. Perfect.
Okay.
All
Yeah,
right.
the only trouble is that I cannot see my cursor anymore, but it's fine. That's okay.
Are you sure? Okay.
Yeah, I don't know, like, so this is probably a bug. And I remember the sequence through which I have to go, like, but I forgot. Like, there was a sequence if I do full screen first and then share or versus the other. Like in one of them, the cursor appears, the other one cursor doesn't. But okay, don't worry about that. Like,
All right. Well, thank you again for joining us. Yeah, and so if you would please let us know a little bit about yourself, and then we'll get into learning from distributed data.
right. So my name is Arya Mazumdar. Yeah, so I just joined UCSD in the HDSI, like Adversarial Data Science Institute, last November. And before that, for a little over 1.5 years, close to 2 years, I was working as a scientist in Amazon while being on leave from UMass Amherst. So before, like even before 2019, I was actually in UMass Amherst, where I spent 5 years. No, sorry, it's not 5 years. It's like more like 4 years as an assistant professor. And even before that, I was in University of Minnesota, where I was like for 1.5 year to 2 year as an assistant professor. Yeah, it goes on and on. Like I have spent a lot of time in a lot of spaces. I was a postdoc before that in MIT, and even before that, I graduated. Like it's like 10 years ago. It doesn't seem like that long though. I graduated from University of Maryland, College Park in 2011. Um, yeah, and my interest has always been in mathematical and theoretical things while being on the realm of applied domains like in engineering. So I was interested in information theory, which is like the science of communication and how do you measure information and so on. And it has some relation to statistics. So lately I became interested in statistical learning, and I started working on some statistical learning and optimization. So what I'm going to talk today is going to be focused on those two topics. So the title of the talk is Learning from Distributed Data. So I will tell you like what are the things I am most proud of in my resume. They're actually my students who have been the co-authors of all of this, all of the things that I'm going to present today. 3 of them are graduating this year, and they all found really good jobs. I mean, last time I was in this type of forum, I didn't have anything next to their name. I just gave that talk. I don't know since what happened, but they got placed. And I have some other students who are incoming, and I have my postdoc Abhishek, who just joined me from after graduating from UC Berkeley. So we have a really a small but really strong group, and we work on all type of problems in machine learning and statistics. With that in mind, let me just go ahead and present some of the work that we have been doing, and maybe you will find something interesting. Okay, so largely speaking, we work on both supervised learning and unsupervised learning. However, we don't differentiate between them too much. So in supervised learning, that's going to be the main focus of today's talk. We're going to talk about something called distributed optimization with information constraints. And all these terms, I'm going to define how all this, what all these terms means, what distributed means, why do we have to do optimization. I think more importantly, what are information constraints. However, we do a lot of work in unsupervised learning as well. Many type of unsupervised learning problems like clustering, community detection is in networks, like some other type of pattern finding in images or other data. We are looking at them from a theoretical perspective, and our thirst has been to basically make some of these methods semi-supervised via crowdsourcing or some other tools. so that we can query, we can do some sort of active learning. We can choose some features and try to query very carefully about their levels. And based on minimum number of such queries, we try to perform this task like clustering or do community detection in some social network and so on. So that part is not what I am going to talk today, because I heard that we have only 5 hours and then everyone has to go to bed. So I'm going to talk about the other part, which is distributed optimization with information constraints. So let me see how we go to optimization and what are these constraints. Okay. And during this talk, I made it very informally. And this is not a super prepared talk. So feel free to stop me anytime and ask me question. I cannot really see the chat for some reason while I'm presenting full screen. I just get the notification. But if there is a question and if anyone wants to stop me, like the moderator, just let me know that this is the question that came up, and I will answer you.
Okay, we'll do that, and I'll let you know if there's anything in the chat.
Sure. Yeah, I got the sense that everyone is typing in the chat and no one wants to speak. And I feel like that all the time when I am over this Zoom meeting, because I have small kids at home, and like anytime I switched on, like I unmute myself to say something, there is someone screaming in the background, and my okay, great. So we are talking about supervised learning. And we all know what we want to do is to predict the future, right? So we want to, there are very big scientific problems in the world, but everything boils down to predicting what is going to happen next, right? Be it climate science, maybe people are working in the stock market, in the hedge funds and stuff, and maybe people are trying to figure out where some galaxy would be 10 years from now. Or they are just measuring some distance. In all of these cases, we are trying to predict something which is in the future. And it turns out that machine learning methods have seen some unprecedented success, right? So in all of these topics in the last 10 years or maybe 15 years, machine learning is being extensively used. And there is tremendous success. I mean, in physics, they usually solve a very complicated set of partial differential equation to predict, say, something where some body is going to be in t amount of time from now. However, they're using now machine learning to do those kind of stuff, and I hear that's working pretty good. Maybe we don't want to, and not all of these are perfectly explainable. So we don't really want to do that in very critical for critical choices, but in general they perform really well, and it's a mystery like why are they performing that well? But we are not going in there. And all of this are prediction from data, right? So this is something we all know. We are all in data science, so we know that this is happening. And there are many things that are hidden under the rug, or basically you use them, but you don't know that that thing is using machine learning, right? For the audience over here, that's probably obvious, but maybe for the general users, they're not. So internet search engines, that's all based on machine learning. So what you are going to do suppose what you are going to search next, and your search engine is showing you a bunch of search suggestions. That's machine learning. Some products are being placed on the side when you do some Google search, or maybe you go to Amazon, you see some sponsored products appear here and there. That's machine learning. I mean, you name it, there are things that were traditionally done in some other way, but we formulate them to be a prediction problem somehow, and then use these sophisticated tools from machine learning, right? Okay, great. So we all sort of know all this. So let's see how prediction from this data, or this learning from this data, how that is tied with optimization, okay? So we want to learn something. So in most of the cases, and again, I think this is a bit redundant, but I will just, for the sake of completeness, I will go through this. And fear not, there will be some mathematical equation appearing. They're just there to scare you, but I mean, they're not really that scary. Okay, so in most of the cases, what happens is you have some information which are called features, right? So you know this. I'm going to make it as ground to earth as possible, grounded as possible. So you have some features. Suppose someone takes my, my cholesterol reading, my pressure, and bunch of other medical things, and then try to predict whether I'm going to have diabetes 5 years down the lane or not. Okay. So you have this bunch of stuff which are called features. I will not. Can you just go 1 second? One of my kids just show up.
Since we're talking about prediction, I can say the professor accurately predicted that he would be interrupted by one of his kids.
That's right. Yeah. You see, especially when they're back from school, there is no way to contain them anywhere. I'm sorry about that interruption. Okay, so what we do is we have these features that, for example, whether you have kids, what are their ages and stuff, and then you want to predict whether you are going to be interrupted. And that's called a level. That's a binary level. In my case, that's like 99% of the time, especially if it is something important. Anyway, so you have these features and you want to predict something. So you want to find a relationship between the features and the level. So the level is the name for what we are going to predict. So whether this is going to happen or not, that's a binary level. But it can be any other categorical things as labels. It can be a real number. For example, I want to check temperature of 10 different cities, and then I want to predict the temperature in some other city just by looking at them. So that's like a regression problem because the temperature is a real number. Okay, so all we want to do is to find a mapping, and that's the basis of supervised learning. I have some training data from where I want to do it. So in most of these cases, what we do is we parameterize H. We cannot really possibly go over all kind of relation that exist, right? All type of complicated relationships that can exist between features and levels. So we restrict ourselves to some certain classes, right? And for example, maybe it's a linear regression where we try to fit a linear model between the features and the level. It can be a neural network where we just input the features to a neural network and we just get the level as the output. Right? You know most of this stuff. So we parameterize this function in one of these ways. Again, I'm not going to go too deep into learning theory, but that's once you do this parameterization, then what you do is something called a loss minimization or an empirical risks minimization. So you basically try to predict from your training data. You use this one of the functions from this parameterized class of functions. You want to predict what the level is going to be. Then you try to measure some loss between the actual level and your predicted level. In the case of the regression where you have, say, temperature, you can just have a L2 loss or maybe L1 loss. I don't know if you know these terms or like, but these are like some measure of how far you are from the actual predicted levels. How far are the actual levels are from the predicted levels, right? So you define something called this loss function, right? So once you have this loss function, you just take the average of the losses over all the data that you have in your training set. And that has a fancy name, which is called empirical risk minimization. So you see over here, I have a minimization problem at the bottom because I cannot find the cursor. I cannot really point to that, but it is minimized over some W where W is a vector. And then I wrote some sum over I going from 1 to n if I W, where this is the sum of the loss. Right? So this is how optimization is connected to learning. All I want to find here is a W. Once I find the W, I find, since the function class that I have is parameterized by this W, I found that function. Now I'm going to use it to predict the future. Whenever I have a level, I'm going, whenever I have a set of features, I'm going to use this function to predict the level, right? So this learning part in here is really minimizing some function, right? and minimizing, or that is actually called optimization. So the learning part over here is just an optimization problem. Okay. And there are many ways we can solve this type of optimization problem. So there is also a fancy and more general way to view this type of things, which is called, which is called stochastic optimization. I'm going to come to that shortly. So optimization in machine learning, bottom line, so far what I have told, is this is the main tool in learning a model, right? And maybe what kind of optimization method we are choosing has something to do with the success of the machine learning models, right? So we have shown you some pretty pictures of, physics and astronomy and bunch of yada yada. And I said that it's not completely explainable why a machine learning model is going to do so good over here. And it performs, like, it basically breaks the barriers that are being set by traditional learning theory. So it does something which is called overfitting. So it fits very large models, very, very large models, but it still performs pretty well. And as a matter of fact, it has been seen in many experiments when they keep on growing the number of parameters of neural networks, which is a special type of models, and many of you are working with them. Actually, it gets better and better. The prediction accuracy of prediction is getting better and better. This goes against some principle called overfitting. So there is one conjecture that learning theorists now make, is that maybe what optimization method that we are choosing, that has something to do with all this, right? All this success. And we actually choose some very specific optimization method. I'm going to come to that optimization method shortly. Okay. And that optimization method is called SGD, or stochastic gradient descent. So if you are training a model, you know what this thing is. So we have an optimization problem. Again, I have on the top, I wrote a minimization problem. I have some function that I am trying to minimize. And gradient descent, again, there is a bunch of symbols over here. If you are averse to mathematical formulas, let me assure you, this is nothing fancy. So you start with some initial guess for what your model is going to be. And then what you do is we define something called this loss function, right? You take a gradient vector of the loss function. What is a gradient vector? Again, I'm not going to go into too deep into it. We are basically going to see how that, what is the direction, what is the directional flow of that function. If we plot that function in a curve, or if you plot that if it is a two-dimensional function, you can plot that, you can have a 2D plot. But more often this is like hundreds or thousands dimensional functions. So you cannot really do a plot, but you can still think of 2 or 3 dimensions that we can visualize. And we have certain form of this function, right? So we want to go towards the minimum of this function. So we take a derivative of the function at certain point, and we go towards the opposite direction of the derivative. So the direction where the function is not increasing. And we take a little steep step there. So that's where this middle box over here is. We start from some initial guess, then we keep taking little steps towards the opposite direction of where the function is increasing, right? And we have to do it locally. We don't have a global viewpoint of the function. So it might end up being a local minima, not the best possible optimum model, but we still do that. It turns out that there are certain functions where there is no global or local minima. All the local minimas are global. They are called convex function, for which we can give actually certain guarantee that the stochastic gradient descent method is going to succeed. Now, I actually hit something. I said that I'm going to take a small step towards the direction opposite to the gradient or the derivative of the function, right? I don't really, in SGD or stochastic, that's what gradient descent is. In stochastic gradient descent, I don't really do that. I actually randomly take a step, okay? I just want to make sure that in expectation, I'm taking a steps towards the negative of the gradient, okay? Again, if it is getting too involved, just stop me anytime and ask me a question. So that's That's what the method of choice is. It turns out that this particular method of optimization, and if we use this in conjunction the uh, with the empirical risk minimization, does wonder, right? It gives you very good performance in machine learning. Okay, so now the general form of this stochastic optimization problem, I throw in a bunch of more symbols over here. So it turns out that, well, let me just keep this slide. We'll come back to this if we need this, okay? Okay, so now this type of optimization problem and stochastic gradient descent that has been well known, and we can all deal with that. People knows this from the 50s. There is convergence result for stochastic gradient descent for convex optimization problem known really long time back. Some version of stochastic gradient descent has been used all the time. So what is the problem? We can, like, as practitioner, we might want to think we have an optimization problem and this is the solution. Work. So what changed in the last 10, 15 years? Well, one thing changed is the scale of the data. Now I have 3 new images to show you 3 new applications, and all of these things are incredibly data intensive. As we have, every one of us probably have seen this type of charts before, which shows the total data worldwide, or the total internet traffic worldwide. And it is growing exponentially, of course. Yeah, and so this is in the scale of zettabyte. If you know what that is, basically 10 to the power 21 bytes. So it turns out then that the total data globally that touched 1 zettabyte only in 2012. And now we are basically in 64.5 zettabyte. The internet traffic, Cisco basically reported that reached 1 zettabyte in only 2016. Right? So we are basically, since then, we are growing like crazy. Okay. So if you have that much amount of data, then when you are trying to do this optimization, you cannot do that in one place because your memory use will not be able to handle it. So there are 2 aspects of handling data in doing this type of optimization. So you want to do a large scale optimization with many number of parameters, but you are basically doing a sum. You remember we had a sum over I going from 1 to n, this loss function. That sum is actually, it contains incredibly large amount of things, right? So what are the 2 paradigms over here? So one thing is that you cannot fit all those data in one place. So, and again, there is a traditional solution to that, which is distributed computation, right? So you have to, and those of you who use Python libraries and stuff, you know that, like, you dream and sometimes you shout CUDA. So there are, you basically distribute your whatever function computation you are doing, right? Especially if it is data intensive. So you have data from a central place, you basically distribute it to a bunch of different worker nodes. So that's traditional distributed computation, because you cannot do all this computation handling all this vast amount of data in one place. Okay, so that's distributed computation, but there is something else at play over here as well. That is, maybe you do not even have all this data in one place. Maybe your data is spread across the globe. Maybe they are in, 1,000 different mobile phones, and you still want to train a model, right? And that is something called federated learning. So you have some central server or a central place that communicate with all these mobile nodes or worker nodes. However, your data is sort of distributed everywhere. And your data is not centrally in one place. So it's not like you can actually, you may not even, so for traditional distributed computation, you do have a chunk of data with you and you can choose to distribute it. Here you do not even have that choice. It is already distributed. Okay. So data is inherently distributed. Right. So, so distributed computing and data parallelism. So this leads to a very specific topology of optimization. So of this empirical risk minimization with stochastic gradient descent. So we want to train a model, but this type of distributed setup. Right. So here is the picture of how this is going to work. So we do have a central server, okay? And then we have these worker nodes. Now, I call them worker nodes. They probably are not working for me, right? So they are just individual nodes. Maybe they are just mobile phones. There may be a tablet or something. Or they might be just EC2 or some cloud computing server. Like in both of the cases, so this is basically just abstraction of both the scenarios. So I have a central server, and then I have a bunch of worker nodes, right? Now, the data is basically distributed across these worker nodes. Okay? So I do have a model at the central server. I do have a model that I want to train. So I start with some initial model. So what I do is I basically broadcast the parameters of my model, my initial choice, to all of these workers. And the workers, then what they do, they basically compute the gradient of the loss function, but only on the local data that they have. Okay? And then they send us back the gradients. Okay, so now what I will do is at the central server, I'm just going to aggregate those gradients and update my model. Why would this work? This would work because of the very specific structure of SGD, stochastic gradient descent. Because this aggregation, I'm just going back over here, sorry, the empirical risk minimization problem, you see what I'm minimizing is basically a sum. Now, part of this summation is being done in each of these local nodes, right? But overall, when I take expectation or I do the averaging, that's a linear operation. So if everyone does their averaging locally and send me back, and then I do a weighted average, I can get back the precise gradient because the gradient operation is also linear, right? So I can find out this unbiased estimate of the gradient, and I can use that to update my model using SGD. Okay. So that's the scenario. Okay. Any question regarding this topology? So we are going to talk about this distributed topology. If you don't ask me any question, I will assume that I tell my students as well, like I'm doing a fantastic job. And don't tell me anything when you do your evaluation. Okay. Yeah, anyway. So this is the setting. Now, when we do that, there are some unprecedented challenges that come that was not there when we were doing traditional optimization. Okay. So what are these unprecedented challenges? So let's see. So by the way, this is how our central servers send the parameters, workers compute their local gradients, send back to the central server. Central server aggregates the results, the local gradients, then updates the model. Okay. So one issue is that this talking between central server and the workers, that has to go through a channel. And this channel is bandwidth limited. So even in the case of distributed optimization, this can create a bottleneck. Why would this create a bottleneck? Because you think the number of parameters of some large models like GPT-3, which has, I don't know, 175 billion parameters. So the gradient that you are sending back and forth has dimension 175 billion. Right? That's more than like a movie, right? So think of, Avengers, Infinity Wars or something that you want to you are streaming that over some channel, and this has to happen over here, right? So bandwidth limited computation sort of says that previously we were doing optimization in one place. So this is basically an unforeseen scenario because many of these connections might even be wireless, right? So that's communication is an issue. And of course, people have measured how much this mattered, and it matters a lot, okay? So this is a plot that I picked up from this paper called QSGD by Alistair and others. It appeared, I think, in NeurIPS in 2017. So there, So we usually do 32-bit SGD. What is 32-bit SGD? It means all of these gradients. So any real number, you use 32 bits to represent that. So let's look at the curve that says the bar plot that says 32 bits in there. And look at the case when we have 16 GPUs, okay? So, and this is like a training of over AlexNet. So when you have 16 GPUs, this is the green bar over here in the middle. Again, I don't have the cursor, and I need it now. So I'm in this 32 bits thing, and I am in the green bar. So the bottom dark part is the communication time takes to communicate. And the top light part is the time take for computation of the gradient and upgrading the model. And you can see that it basically almost 4:1. So communication is taking way more time. Now you know when PyTorch or something, when you are actually, you give something to train and just wait over the weekend, go back to Monday and it's still not over. This is basically contributing to that. Maybe it would be over in a day, but it would end up taking 4 days because the communication cost is a huge overhead. And that happens when you basically scale it up more and more, when you have a large number of parameters. We don't really deal with billions of parameters on an everyday basis, but this still affects. And who knows, maybe in a couple of years, this will be so mundane that everyone trains billion parameters models. Right now, it's still limited to, OpenAI, and maybe Google is doing some experiments and stuff, but it's bound to become more regular as the price of hardware increases. So this is really a lot of overhead, and we want to get rid of this communication overhead. Okay, so that's one issue that was not there when we were just doing machine learning in MATLAB in one place. Okay.
So before you go to the next issue, there's a question in the chat. The architecture you show with a single central server, is that the same or is that different from all reduce distributed training? Are you familiar with the all reduce name?
I'm familiar with MapReduce. Is that similar to that?
I don't think so. Well, so why don't we?
Can you explain to me what is all reduce? I'm sorry.
Yeah. So Vladimir, if you want, you can explain. I think also I'm anticipating that Professor Mazumdar is about to show different ways that you can do this instead of just this one central communicating. And so maybe.
Oh, no. Yeah, actually, that's like so you can have a decentralized setting. Actually, part of MapReduce is actually this decentralized setting where you do not have so I don't know, I suspect all reduce is, I don't know, some offspring of MapReduce, or maybe it is related to this, but it probably doesn't have this type. So when you do clustering, for example, or some other data mining tasks, you can use MapReduce. Or suppose you are trying to solve some graph problem, like finding spanning tree or counting triangles and stuff, right? You can use MapReduce framework. And many times you do not need to have this central server and many different servers. People can, or servers can work in a completely decentralized way. So the picture that I showed, that's like one particular topology, and that's precisely why it is called federated learning or federated topology, because there is one central server. But communication is going to be an issue. Depends on how big your problem is in other decentralized learning problems as well. Because so here, there is no direct link between one worker nodes to another, right? So, but you may have that, and then that would be some communication overhead as well.
Yeah, hi, Arya, this is Vladimir from UMD. Long time no see. I just because I'm doing something with
Vladimir from UMD.
Yeah.
Oh my God! Are you in San Diego?
Say it again.
Are you in San Diego?
No, I'm in Maryland, but I monitor what happens in the world. all around the world. We can talk we can talk later after this. It's been a long time. So I just because I was looking at TensorFlow and they have mirror strategy, distributed strategies for training, and they're discussing this is for GPUs. So we have multiple GPUs and they have this NVIDIA link, and then basically you exchange the gradients. So each GPU sends the gradients, its gradients to the other, and then they exchange it. Then there's some averaging, and then this is again distributed. So there is no centralized thing. It's
that's decentralized. Yes.
Yeah, it's the distributed. Yeah,
but the communication problem is still going to be there. I mean,
right.
Something, but this is okay. Yeah, we should can you shoot me an email or like do something?
Yeah, right.
Okay, good. Yeah, let me go to the next issue. So here is like one solution, possible solution to the problem, and then I'm going to go to the next issue. So instead of sending the entirety of the gradient, why don't we just send a few bits? Okay, and I'm going to tell you what those few bits can be a bit later. So when we do that, there is like an entirely new theory of optimization we need, because now we don't only have to show that stochastic gradient descent converges or stochastic gradient descent does well. Like in practice, we have to show that by instead of sending say 100 bits, we are sending only 20 bits or 10 bits. That basically reduces the communication cost by say 1/5. But we have to lose something in performance. And is that loss going to be significant? Can we give some theoretical guarantee on that? And also in practice, how would it work if I, instead of doing this gradient descent, if I just send few bits of gradient and somehow make the central server just work with this? Same solution is viable for this decentralized setting that Vladimir is talking about. Instead of exchanging the gradients between, maybe you exchange few bits of the gradient. However, we don't, like the analysis that I have done or like my group has done is for this federated setting. The decentralized setting, I think there are some work. So for every type of graph topology, there can be, different results. Okay, so what is the next issue? So the next issue is something wrong can happen, right? Because not all of these machines are in your control. A machine can be just rogue. There is this big issue of adversarial attacks in machine learning. Maybe someone has just changed the levels of your data just so to screw up your final model. So you trained a model and someone just adversarially changed some of the levels, right? Is your model going to be robust to that? And people have shown that even with slightest of this type of things, a model can be completely wrong and it will do very bad predictions. And maybe you have seen these pictures where they just change a few bits of the stop sign and the driverless car will take that stop sign as something else. And it will probably go. And that's like a life critical scenario where your car doesn't stop at the stop sign anymore because someone came and signed their name in the stop sign. Okay, so adversarial attack in machine learning is a big deal. And if you think of this distributed scenario, that becomes like an even more critical situation because not all of these workers are with you. Think of this federated learning setup where you might have mobile workers, so maybe you are crowdsourcing or doing something in someone else's commodity hardware, and they can be adversarial and they can, there are different type of attacks. There is a community that basically designs this type of Byzantine nodes and Byzantine attacks and see what kind of change is going to be in the model. So that's another issue, right? And adversarial attacks in ML, it's a well-studied topic. And there are different type of models that people assume. They assume that there are maybe two of the working nodes are not working for you. They're going to mess up the model. And they maybe can collude and they can figure out a strategy to do that, right? And they can be very sophisticated as well. Maybe they have some computational strategy they are going. So there is something called saddle point attacks that they can do. It's pretty hard to beat because, all these gradient descent points, they are going to get stuck in some point where the value of the gradient is very small. Even if you go to more complicated method than gradient descent, it's going to go to a point of zero gradient. That means the loss function is basically not changing over there. But that doesn't mean that this is a local minima, or even a global minima. I mean, global minima would be, that's what we want, but may not even be a local minima, because it can just be a saddle point. And it has been shown that adversaries can collude to basically take your model to some saddle point, right? And your model is then going to produce something which is garbage, but you would have no way to know it based on the training data. Okay, so this distributed setting, especially when you are, is more susceptible to this type of attacks. Right, those are the two issues. Third issue is a user issue. Why would someone share their data with you? Maybe the data, you have some bank statements or something else. You are trying to do something, predict some housing needs, and you want to look at some bank account amounts or some other type of features that no one wants to reveal to you. Maybe this is medical data and you are doing something for some prediction. And during this pandemic and stuff, this became even more crucial. People are not going to really share with some third party who wants to do some data analysis what is their diagnostic history throughout the past. So they are no way they are going to do that. So they need some privacy. So you need to assure them that I'm going to do this distributed computer. I'm going to take your data to train my model, but I'm not going to look at your data. How do you give them that assurance? Is there any way you can guarantee that? And that's part of this learning process, right? And you can, in this same setup, you can have this as a very big problem. Okay, what else? So privacy in ML, it's again really a big topic. So how do we not share data or identifiable information, but be still useful in training? So there is something called differential privacy, which is a measurable quantity of privacy. And again, we want to see if we give guarantee of certain type of privacy, is this going to affect my model training? Is the stochastic gradient descent algorithm that we have designed still going to converge? Okay, what else can happen? A machine can just be slow, right? Like there you are a bunch of machines. They might not be adversarial, they're just slow. And it has been shown in, again, many experiments. So this is an experiment that was done in Amazon EC2. They take basically, I think, about 50 different servers, and it turns out that there are 10 of them that are really slow. The response time is much higher. So what do? Do we just not take data from there? So this is actually, we have these stragglers. How do we deal with that? So these are questions. Slow machines, adversarial attacks, need for privacy, bandwidth limited communication. So if you look at traditional optimization textbook, they're not going to talk about these things. However, when you are using optimization to train very large machine learning model to learn from distributed data, this becomes important issue, right? So we want to deal with that. So now for at least a couple of them, some of them, maybe let's say 3 of them, the communication needs for privacy and adversarial attacks, we are going to give you an overview of some solutions. So let me just check the time. And is anyone keeping the time? How far, where are we right now?
Yeah, we have another half an hour for the scheduled block.
Okay. So I will take about 10, 20 minutes or so. And again, feel free to stop me. Okay, so this is the setup of the problem that we are working on. Okay, so all this basically fits into this optimization with information constant. So we are trying to do some optimization, but we are trying to do this when information is limited. We are trying to do this when information is obfuscated, maybe because of privacy. we want to do this when wrong information is communicated to us, right? So this is the optimization with information constraint. So let's see how we can achieve both communication efficiency and privacy in this SGD type of problems. Okay, so recall we are trying to minimize this sum. Previously I have average, but I mean minimizing a sum and minimizing the average is more or less the same. And this is our setting. So we have the gradients coming back from the machines, right? So let's, instead of stochastic gradient descent, let's think of gradient descent, and this is what is going on. Like the central server is sending the machine the parameters, and the machines are computing gradients in their local data, sending the gradients back. Now, this is how gradient descent work. And what we are going to do is federated averaging of local gradients, okay? So when you have a local gradient, what you want to do is you want to send it, right? You want to send it to the global server, the central server. It is known that as long as you are sending an unbiased estimation of the gradient with certain variance, certain error, the SGD, the stochastic gradient descent, is actually going to converge, right? So what you want to do is to compress the gradient, and the gradient is high dimensional. So transformers, like now this is like not even GPT-3, like the usual transformer, they use something like 200 million parameters. So your D is that much dimensional. You want to squeeze it into few bits. Okay. So what I'm going to, like this problem is, again, it's pretty well studied, starting from that paper by Alistair et al. In 2017. There are a bunch of papers, and we also have our contribution, our list of papers over here. So the properties that we are going to use is stochastic gradient descent converges for convex function, although like neural network is non-convex, but let's not go there. As long as we are sending unbiased estimate of gradients. And the rate of convergence depends on the variance of the unbiased estimator. So we want to do something like a data compression. We have a local gradient over here, which is D-dimensional, D is very high. We will have a quantizer that's going to fit it. Now this quantizer must work very fast. We take that gradient because we don't want to add up computation time. So we cannot really look backward like, oh, there is JPEG and they do a bunch of compression. So why don't we use that same protocol over here to get, first of all, we have so all the literature in compression that's designed for some very specific type of signals like images or videos or speeches. What we have here are gradients, right? And gradients don't really follow the rules that images follow. So whatever your compression techniques for one image or maybe your videos, that's not going to be useful when you're trying to compress a gradient. And secondly, you cannot really come back from statistics information theory and say, oh, I'm going to use this optimal quantizer because this is statistically great. No, we want to think about computation, and I'm very much computationally limited, so I want to do something super fast, maybe linear time and not even that, sublinear time. So I want to just do one pass on the data and come back, throw out on the gradient and throw 4 bits or 5 bits and say, let's send this. So I don't want to add more overheads. So all I want to ensure is that on the other end, again, I will be able to very fast reconstruct something, which is this G hat, such that it is an unbiased estimate of the local gradient. As long as that's happening, I can just aggregate, it will remain an unbiased estimate, and the SGD is going to converge. So there are certain randomized mapping that we can do to do this. Actually, I'm not going to go into the compression algorithm that we are going to use, but think of this. So one possible thing is to just send the signs. So you have D-dimensional vector, instead of just the real numbers that you have, just send the signs. Okay, just send the whatever is the sign of the coordinates, plus or minus 1. okay, 1 bit per coordinate. And then just run SGD with say plus minus 1 in place of, like, you have a binary vector which can have +1 -1. Just take a small step towards that direction in your SGD. And it's called sign SGD. So what we are going to do, what we do actually is more sophisticated than that, while being more or less same convergence rate. So there are certain other techniques. So basically, so this is sign SGD is what we just told you. There are other techniques like QSGD. It's like more than, it's basically, instead if you have D bits, D, a real vector of length D, it will reduce it to square root of D bits. Okay, so QSGD is pretty good. So we can actually drive it down even deeper. And we propose something called VQSGD, a vector quantized SGD. Turns out it works pretty well. So there's some small experiments that we did with MNIST, fashion MNIST and CFAR data set. It turns out that they converge. The convergence rate is almost similar to whatever if we have done full communication. So we have not done an experiment with billions of parameters, because that would require, that's like going out of academia. But if any one of you want to give me cloud, I have the codes to run it. So turns out that you have 10,000, there are like 100 by 100 images. So it's basically 10,000 dimensional case. You can reduce it to say 2,000 bits. So 5-fold reduction in communication, and it performs really well as well. Okay. So number of bits per machine per iteration, instead of 10,000 real numbers, we are sending only 2,060 bits, still converges, maintaining the rate. So we learn a pretty good model. So this is what we are individually quantizing the gradient, but stochastic gradient descent is actually a process, right? So in each iteration, you get new gradients, you compress them. So what I just told you is independent, it doesn't look behind, like what are the previous gradients. So it turns out that you can do something over there, and that's really good for non-convex optimization. So you can look at your previous gradient and you take the current gradient, you look at some running difference between these two gradients, quantize only this part, this error feedback. You can send even less number of bits and your performance remains the same. So this is something called error feedback that improves why is it called error feedback? Because whatever is the quantization error in the previous step, we are basically adding that up to the current gradient and quantizing the overall thing. So that algorithm performs pretty well as well. And we can have some theoretical guarantees of this as well. So that's how we deal with communication. So let's talk about privacy. So what is this notion of differential privacy that people came about is this. Suppose, since we just have gradients, and how are we revealing data? So local machine, suppose I have my data and I compute my local gradient. I just don't want to reveal this local gradient to you, because then you can probably infer something about my actual data from the gradient of the data. So I want to prohibit that. So what I can do is I can make my gradient noisy. I can add some noise to it so that you cannot really figure out what my data was. But in general, I maintain the direction so that it is going to mess with the convergence of SGD, but I want to find out the sweet point where I can give optimal privacy guarantee, but at the same time, SGD will still converge. Okay. And it turns out that there is a quantifiable notion of privacy, which is called differential privacy. So let me not go into the definition, but the method that I have just shown you, the quantization methods, they actually give us some privacy automatically. Why? Because of the following reason. When you are quantizing some data, you are obfuscating that data anyway. Think about the sign SGD method, where you have a vector And you are just, instead of sending the values of the coordinate, you are just sending the signs of the coordinate. That amounts to adding noise, or that amounts to obfuscating a lot of your data. So when you are quantizing, you are actually getting some privacy for free. It turns out we can actually quantify how much privacy you are getting for free. Okay. So when someone looks at that data, they cannot really reconstruct that quantized things. They cannot really reconstruct your data. So think of it that way. Like, suppose you have a bunch of images, and you do some gradient computation on those images, you get some vector, you quantize it, whatever you have, no one can look at that thing and get back to the images that you have. However, they can use that thing in their SGD algorithm, and the algorithm is still going to converge. It's going to be useful. And in practice, this works. Okay, again, there are certain values. Let me not go over. So this basically says that we have certain quantifiable measure of privacy, and at the same time, this converges. Let me tell you one other algorithm that that works when you have this adversarial errors, adversarial attacks, or Byzantine attacks. So when some of the worker nodes that you have, they have gone rogue. Okay. So this is the same set of equation SGD that you have seen before. Now there is only a little change. So I assume that I have capital M number of machine, and each of the machines have certain amount of data with them, a little n amount of data in them, right? And there are a fraction of the machines that are adversarial. So they are Byzantine machines. So they are going to send you really bad information. Okay, so this is the setting. So machine 2 is, for example, bad over here. It's not going to send you actual gradient. It's going to send you something else. Okay. So here is how you do a robust upgrade. So recall that the central server is getting back all the gradients from the different machine, and then it takes the sum of them. So what we do is a norm-based filtering. So we look at the value, the norm of all those gradients, and if we basically trim some of the values that are really large, okay, and we keep the values that are small or average. We do the aggregation with only those gradients. Why is this going to work intuitively? Because if the adversary has put a lot of bad things in the gradient, like if it has increased the norm of the gradient by a whole lot, it's going to get filtered. So if you have too much noise, that's going to get filtered. So only time you are going to count that in when the noise is small in norm, right? It can still mess up your thing, but we can probably show, and in practice show, that that's not going to be the case. So in different type of different type of convex and non-convex optimization, this turns out to work. Let me just show you the plots. So in this case, so there is actually the type of attack is a random attack. So random, a level shift. So this is again on MNIST images, that each MNIST image has a level from 0 to 9. If you are familiar with that data set, these are like handwritten digits. So instead, you just do a level shift. Instead of 4, you basically change it to 6. When 6, you change it to 8. That's called a deterministic level shift. You can do a random level shift as well. In both the cases, for this type of adversarial attacks, actually the SGD with our filtering algorithm, that converges. So in practice, there can be more complicated plots. So you can have a more complicated type of attacks that people have come up with. Some of them has to do with this saddle point thing that I mentioned. So that actually, so we show convergence beyond the theoretical bound. So we can get some theoretical results, but in practice, the algorithm works like a charm. Okay, so it works on ReLU nets with MNIST and CFAR. That's the kind of experiments that we have done. Okay, so in the interest of time, let me just not go to this stop at the yeah. So we don't stop at here. So stochastic gradient descent or gradient descent is just a first order method of optimization. You can have a faster method that requires less round to converge. That's called Newton's method, but that requires computing the Hessian. Okay, so if you are using something like, there are like second order methods are also being used, and that's just now it's escaping like what package would have that. But anyway, so there the problem is that it is not as parallelizable because there are some non-linear operations. So in SGD, everything is linear operations, highly parallelizable. Second order methods not parallelizable, but they are very fast. So we can actually parallelize them. And the bottom line is they also work pretty well. Even in the presence of Byzantine adversary, you can also control the communication. You can actually take care of privacy. All these things works for second order methods as well. And they give really pretty good results on smaller scale. Again, we have to do some large scale experiments to see how they perform really well. Whether they perform really well or not, my conjecture is they will, because that's sort of the indication is. Okay, so what is the outlook from here? I mean, theoretically, there is a bunch of things to do. So we don't have much theoretical results for non-convex problems. So non-convex optimization is a big thing. So if we can get something that deals with that. So this privacy thing that like we want to look at other type of problems such as clustering or something else where we have this privacy. We want to see whether our methods or privacy preserving methods, whether they work there or not. So there are plenty to do, and like in practice, there are a lot to do because we have not run a whole lot of large scale experiments. We did something with our cloud, whatever access we have, but that's like, I mean, that's going to be really the litmus test for all of these algorithms. Yeah, so there is the bunch of papers that have been appearing in this machine learning conferences in the past few years. Yeah, well, that's basically it. Maybe I will come back in some other time and talk about the semi-supervised and unsupervised learning problems, which is just learning from data like clustering and so on. But that would be something for some other time. Thank you so much for listening to all of this.
Thank you. We still have not solved how to do applause on Zoom meetings. So people can do reactions, but that's about as close as we can get. All right, thank you. I have a couple questions that popped to mind. I really enjoyed the talk, but let me first open the floor and see if anybody else has questions they would like to ask.
I see that. Okay.
All right. So give people a minute to think here. I'm going to ask you one question. So I thought this was a nice talk. Things built up. Regarding the privacy, I wanted to ask. So we are sort of obfuscating the data so that we get a certain level of privacy on what we're sharing. Has anybody done research to look into if your central server has an adversary, whether or not they can adversarially send you parameters so that you are actually exposing more of your data than you intended?
Okay, I don't think so. I don't think that like people have thought that way. If central server is compromised, that's
or man in the middle, such that you think you're talking to the central server, but you're actually talking to an adversary, something like that, right?
Right. I mean, yeah. So here is one thing you can do. Like you can suppose you have your data in your mobile phone or in your computer. You wouldn't share like before that privacy is like the shield that you have, the the noise that you are adding or the obfuscation that you are doing. So in most cases, this will not depend on the parameters that are being sent to you. See, it is not adaptive to those. Now, if it is adaptive to the parameters, maybe you can do something more clever, right? So because it's adaptive, you know, you have more information, maybe whatever is the encoding scheme that you come up with is more well informed. But then there is the risk that someone has sent you, you know, compromised parameters, so your scheme became incomplete. So I think one solution would be to not let it depend on whatever are the parameters that are sent to you. So you have some differentially private schemes. So there are something called matrix mechanism where they basically just changes thing in a random way. So the notion of local differential privacy, this is very interesting, and I don't know whether, so this goes back quite a bit. So suppose, here is the thing. Suppose I'm giving you an example from 1960s, okay, and the first paper that came up with this notion of local differential privacy. So you want to just estimate how many the proportion of the US public that are members of, say, Communist Party in the 60s during Cold War or something. If you can try to do a survey, but if you go and ask anyone, no one is going to give you the right answer, or maybe a lot of people are not going to tell you the truth, whether they're members, especially if that thing is underground. But we have to do this type of survey all the time. What is the guarantee that when you know, there is a census and like it's going to some government agencies, and who knows, like what are they going to do with your data, even if they say that they're not going to use it in this purpose, right? So, but this is crucial that we estimate, or maybe some disease, like how many people have this disease, what is the proportion? Maybe I don't want to disclose whether I have that or not, right? Or my race or ethnicity. For a variety of purpose, I want to keep it to myself. So what I can do is I can come up with, so here is what I am going to do. So I'm going to, you ask me a question, I'm going to toss a coin. If it is heads, I am going to give you the correct answer with 75% probability. Okay. So I will have two tosses. So one is an unbiased toss, and then I will do a biased coin toss, and that's what I'm going to do. If it is tails, I'm going to do something else. I'm just like taking the number, like random numbers from my head. And now if you do this calculation, assume that the proportion of the people, now you aggregate this result, whatever are the numbers that you have gotten. So everyone has some plausible deniability, right? So they can say that, oh, all the information that I gave is based on some coin toss, so you cannot really get to me based on that, right? So you have that deniability. However, if you just do a little probability calculation, you can see that even from this type of thing, assume that the proportion of something like people being infected with some disease or being member of some party, something is some P. And then just do this calculation. And when you do the aggregation, you will see that you can go back and find out this P. You cannot really go back to the person. You can get a prior probability, but you cannot really charge anyone based on a probability, right? And you can make those probabilities pretty close. I mean, 49% versus 51%, and you can still get this little P. So what we are going to do is something like that. So all we need is an unbiased estimate of the gradient, right? We do not need your entire data. So you can obfuscate your data a whole lot, do a bunch of this random coin tossing, and then give me just something so that I can get that sufficient statistics. So that's what we are going to do, and not rely on, you know, what the central server is telling me.
Okay, great, thanks. So throw in some differential privacy on top of the quantization, and then should be fully.
Basically, this quantizer actually, they can be combined. It's not like they are conflicting things, Because when you're quantizing, that's automatically does some of the work that you need to do for differential privacy.
Mm-hmm. Yeah, thank you. Okay, we have 5 minutes, so I think we have time for 1 or 2 questions. If anybody wants to ask a question before we run out of time.
There is one person who said, yeah, Newton. So
I have not used second order methods, not just in my, you know, regular TensorFlow, PyTorch training loops.
Right. I think gradient descent or stochastic gradient descent is very stable. I think there are 2 reasons. Like you can throw a lot of things at stochastic gradient descent, it's still going to converge. And that's what we saw as well in this talk. Newton's method, not so much. It's faster, but it will not. Maybe it may falter when you throw this much garbage at it. So that's definitely one of the reasons. Another thing is this parallelizability. So in Newton's method, you have Hessians, right? And you take inverse of the Hessian. So that's like a matrix inversion. So everyone, like in the with the local data, you can compute something like a local Hessians. When you take inverse of that, that's like inverse of local Hessian. But you cannot really add them all up to get the inverse of the global Hessian. That's not inversion. Matrix inversion is not a linear operation. So you sort of like the theory is dicey. How do you make it distributed? Yeah, but quasi-Newton methods are out there. I think there is just like that. I'm just searching for a package which you could. Yeah, anyway.
Okay, anyone else?
I mean, you know and stuff, right? So yeah, I mean LBFGS. So which basically compete with SGD, but I think SGD is still the choice, like method of choice. Okay, I think there is no more questions. So
I have just curious from practical perspective. If you let's say if you have a mini batch gradient descent, you're going to smooth the gradients. This probably will help for the compression and make things works for the privacy.
Right. Actually, they do that. So in mini batch, how do you compress? There is something, this gradient smoothing. Right. Yeah. That's like there. I think I have seen papers that, so for mini batch or like local STT, where basically you take some steps locally. You do local gradient descent, local gradient descent, and then only after a few steps you send back your local gradient. That's another way to minimize communication. Right.
Yeah, and I mean the TensorFlow and PyTorch packages now have distributed training functionality in them where, you know, whatever, every epoch or whatever, you know, every so often they communicate. I'm not sure that those have the theoretical guarantees, but in practice, as you say, right, on average, it is the gradient in expectation. And so,
right.
You know, it tends to work out fine, but in reality, it's not exactly the same because, you know, especially if one, like you said, one device is slower. So if you have 5 GPUs and one of them is older and slower, then it's not really operating on the same data and it's not updating with the same frequency. And...
there is a very big issue that I didn't talk about in this distributed setting is heterogeneity. I mean, data can be like, we are trying to fit one model for all. So that's, that probably is not a great idea to begin with.
Yeah. But I think for most people, they find that if you're just you know, classifying X-rays as cancer, not cancer, even though you don't necessarily have the theoretical guarantees. Most of the time, it works. So you can get the performance boost by, you know, distributing over more devices, even though you're not necessarily doing it exactly the way the algorithms say in order to have the theoretical guarantees.
So there is, I think they use something like SignSGT or some, there is this Amazon MXNet. So this NVIDIA collective communication library, so NCCL, so that employs gradient compression. So that uses a bunch of similar techniques to do gradient compression. It's like, yeah.
Well, that would be good because obviously the more frequently you can communicate, then the more, I don't know, I'll say the more true you are to the algorithm. If you go off and compute an hour, you know, giant mini batch, and then you send back that update to the central server, I mean, you know, you may be pretty far off on your parameter updates at that point. So you want it to be frequent, yeah, high volume updates both directions. Get rapid convergence. Yeah. Okay. Well, thank you again. Thank you very much for your time. We love getting all these different perspectives. We love hearing about the different research, and hopefully this will spur people to you know, learn more about this topic and perhaps follow up with you if they have questions on the topic.
Feel free to reach out to me. I mean, we are in HDSI is very, as you know, is very industry friendly, and we want to be practical. Although we do a lot of theory, but we also want to be grounded and you know, look at real problems and work with everyone. So feel free to reach out to me if you have anything to ask, or if you just want to collaborate. So as I said, there is a lot of data mining style thing also we are working on. So yeah.
Okay. Well, great. Thanks everyone for joining us, and look forward to see you at future HDSI speakers, as well as, you know, our Saturday office hours and our various other webinars and our upcoming book club. So thanks everyone. Good night.
Thank you for inviting me. Thanks.
Thank you.